All right, so here we go for the second part of chemical kinetics. So when we left off, we were talking about rate laws and instantaneous, the initial rate. And so that works well in a lot of situations, but as I have written here, it does not work well universally. So when we are looking for a universal solution, we need some mathematics specifically concerned with change over time, which is the domain of calculus. However, I'm going to tell you we are not going to be doing any calculus, so don't worry. I will say, though, that by integrating the rate laws, we can arrange them in a linear equation format, and this allows us to use experimental data in order to determine the reaction order, because based on the concentrations, we can plug them in to the integrated rate laws, and if they come out as a linear graph, then we know that that is the correct reaction order. So to look at the rate laws, right, if we have a first order, right, or that the rate is dependent on the concentration of one thing, right, one thing to the first power, that is a first order rate law. And we can arrange it after integrating into a linear equation that will look something like this, where we have the natural log of the concentration at time t equal to negative kT plus the natural log of the concentration at time 0. And this should probably look kind of familiar from talking about half-life in the nuclear unit. Now for second order, right, we get something that looks like this, where we have the rate is equal to k times the concentration of something raised to the second power, or conversely, we could have k and a and b, where we have two things, and that would also give us a second order reaction, but we will talk about that in a moment. And I don't know why I have the natural log in here, because that should not be natural log. So I was talking to you, I was flipping through my book because I thought that that was not correct, and it's not. We should not have natural log in there. Okay, so that's first. And second, there is also something called zero order, where if you notice, the rate is not dependent on the concentration whatsoever. And so here, right, we do not have the natural log of anything, and we just have our concentrations starting and at time t. Okay, half-life. Half-life is a reaction rate kind of thing. For first order, this should look pretty familiar, all right, where the half-life is equal to 0.693 over k. Hopefully you all do remember that, or that k is equal to 0.693 over half-life. Either way, in this case, right, because the half-life of a first order reaction is independent of the initial concentration, concentration does not appear in the definition of the half-life for a first order reaction. However, for second order, because the half-life does depend on the initial concentration of your substance, it appears in the definition of half-life, where half-life for second order is 1 over Ka. Okay, reaction mechanisms. Here is where we start to break down some reactions. So, balanced chemical equations. They give you a description about the species present before and after the reaction. However, they don't really give you any information about the path that is taken to get there, right? So they're not exactly lying to you. They're just leaving out some information, right? They ignore the formation of intermediate species that may in fact be responsible for the rate of reaction, which if you're just looking for the overall stoichiometry, you can ignore. However, if you're looking at reaction rates, you have to look at the intermediates. We will take this reaction for example. So this reaction is the overall process that is going on. You have nitrogen dioxide and carbon monoxide going in, and coming out you have nitrogen monoxide and carbon dioxide. However, if we take a look at the reaction mechanism, right, we have a first reaction here where you form an intermediate, NO3. That intermediate then goes on to a second reaction and reacts with carbon monoxide to form our N2 and CO2. Now you'll notice that when you add these together, right, NO3 appears on both sides, so we cancel that out. NO2 appears on both sides, so we cancel that out. So what we get is this overall reaction, right? Because there are things that appear on both sides in our mechanism. However, in the mechanism, we see that we are making an intermediate, something that is not represented at all in our reaction. And so that's why when we're looking at rates, we need to take into account the reaction mechanism. So before we get into what that all means for calculating and how it affects our rate laws, we're going to talk about molecularity. So this describes the number of species involved in a reaction. You can have unimolecular, so that would be a single molecule, right? Something like this. You can have bimolecular, the result of collisions between two molecules, something like this, or something like this, where you have A and B reacting with each other. Both of those are perfectly legitimate. They happen often. There are many reactions that are unimolecular or bimolecular. There is a third, termolecular, the result of three molecules colliding simultaneously. While this does occasionally happen, it is extremely rare. It is not something that you will tend to see. We can write termolecular as to the third. We can write termolecular as something squared reacting with something else. We can even write it as three things reacting together, right? All of these are highly unlikely to actually occur. And so if you see a reaction mechanism or rate expression that has a termolecular molecularity, it is probably not actually termolecular, and it is representing a actual rate law with what we call an observed rate law. So here we're going to talk about something called rate determining step. So in a multi-step reaction mechanism like the one we saw previously, there is usually only one slow step and the others are considered to be fast. The slow step determines how fast the overall reaction can occur, right? Because it is the slow step, it is happening slowly, so that is where the bottleneck is going to occur. It's going to hold everything up, and so that will determine how fast the reaction can occur. So if we take a look at our previous reaction here, right? Now, if our slow step is the first step in the reaction, no problem. We just write our rate law, right? Our rate is going to depend on the collision of these two molecules here, right? So the concentration of NO squared is going to determine our rate. Easy enough, right? We write that rate is equal to K times the concentration of these things squared. Great, right? They're reacting together, NO2 plus NO2. Fantastic. Easy enough. Now, what happens if in a reaction like this, we have a mechanism? Oh, sorry. So in a reaction like this, right? The rate law that we would write for this is NO, and two of them are interacting with a Br2, right? And so this would be our reaction rate expression. Now, if you take a look at this, we've got 2, we've got our 1 here. That is termolecular, which, as I said before, is not going to happen, is not likely. So what we need to do is we need to take a look at some reaction mechanisms that might allow us to write something that will occur. So we take a look at a mechanism, right, where this is a fast step, and the slow step, unfortunately, involves an intermediate. So we're going to have to take a look at that, right? So we're going to define some reaction rate constants. Okay, so now what we're going to do is we're going to write some rate laws here, right? So the first one that we can write is we can write that rate is equal to K2 and the concentration of NOBr2 and NO, right? Which, great, that is bimolecular, looks good, very nice. However, it doesn't involve one of our starting materials. It involves an intermediate, which is something that we really don't want when we are writing a rate law, right? So what we are going to do instead is write that we have two things that we can say here, right? Rate is equal to K to the sub 1, the concentration of NOBr, and rate is equal to K1 NO Br2, or that K sub 1 is equal to NOBr, or sorry, whoops, K sub 1 NOBr is equal to K1 NO Br, right? So now what we have here is a situation where we can rearrange this to say that NOBr is equal to K1 over K1 NO Br, right? Everybody with me so far? Good, great. So now when we look at this, right, we can put this back into our initial statement, right, because we have substituted some things for our intermediate, right? So we can put it back in here, right? That's what math is all about, substituting some things. And we get K2 is K1 over K1 NO Br2 NO, right? So this is starting to look a lot like that initial rate that we had, where rate equals k times NO squared BR2, right? Our term molecular rate statement here that we said is not going to be the case. However, right, looking at this one, which is going to be the actual rate definition, we have to put it in terms of things that we are putting in that we can initially measure, because we're not going to be able to measure the intermediate because it's happening in the middle of the reaction. So we have something that looks like this, and if we substitute that K2, K1 over K just equals K, right? We rewrite this as K NO squared BR2. Now, that was a lot of work to get from what we said was our initial rate definition, but that couldn't really be what's going on, all the way to saying this is what's going on, but we're going to find a way to express it as this unrealistic rate statement like this, right? Now that I've drawn a ton of arrows and I have scribbles all over this, this is really clear, right? Great. So no further questions are needed. Fantastic. So when I come into class and you come into class, I'll ask if anybody has any questions, and you'll say, no, we understand this perfectly, right? Great. Then I'll see you in class, and we won't have any questions about it.